Hello everyone. Today we'll be going over Griffiths Problem 8.4. We're asked to consider two equal point charges separated by a distance of 2a, then construct the plane equidistance from the two charges, so in this case the xy plane. By integrating Maxwell's stress tensor over this plane, determine the force of one charge on the other. And then for part B we're asked the same, but the charges are of opposite sign. So, you use Maxwell's stress tensor by integrating a flux integral over a closed surface. This flux integral then gives you the force acting on the volume within the enclosed surface. We are asked to integrate Maxwell's stress tensor over the xy plane. To create a closed surface that also encloses a charge, we add a hemisphere that also encloses this charge, and we take it so that the radius of this hemisphere goes out to infinity and it touches the xy plane. Now, if the radius of this hemisphere goes out to infinity, that has some consequences for the electric field, since we know that the electric field scales with 1 over script r squared. So that means that our script r is going to go to infinity, and so our electric field is going to be 0. So that means that the flux integral through the hemisphere out here is 0, and only the xy plane is going to contribute to this flux integral. The elements of the stress tensor are defined by equation 8.17. Noting the Kronecker delta shows up and is defined by this. This is an electrostatic case, so the charges are not moving and are not producing magnetic field, and the problem doesn't give us a magnetic field, so the magnetic field is 0, and that simplifies our stress tensor a lot. Now, by symmetry, the charges are acting on a single axis. They will not be pushing each other in the xy direction. So those components are 0, and we only consider the z component of the Maxwell stress tensor. So if we spell out the stress tensor dotted with the elemental area, it looks like this, with all the elements lined out. We're only considering the z component, this right here, and that looks like tzx dax plus tzy day plus tz daz. Now, for the xy plane, the elemental area is in the z direction. By convention, the area points outward of the enclosed volume. For this problem, we're going to go with the lower part. So for our case, our elemental area points upwards. And this also means we don't have any x or y components of the elemental area, so those parts are simply 0. Since dax, day is 0, these terms are also 0, so we need to figure out tzz, daz. Okay, so when you plug in those indices into our Maxwell stress tensor, it reduces to this. So now we need to find what E is. So I move the charges to a cylindrical coordinate system to make things easier, and I'm looking at the problem in a single plane. For this case, the charges are both Q, so that means that their electric fields are pointing in this direction. We notice that the EZ components are pointing in the opposite direction, and the S components are pointing in the same direction. So the S components add up and are equal by symmetry, and the EZ components are equal and opposite by symmetry. When you add the electric fields, you simply now get 2 ES2. The next thing to answer is, what is ES2? If I look here, the ES component is simply E cos theta, where E is simply Coulomb's law and is the charge due to a single point charge. Then the next thing to figure out is what is cos theta. So then we refer to here. We have A, we have S, and we have script R. And script R is the distance between the point charge and the point on the xy plane. So cosine is just going to be S, the distance from the origin over to the xy plane. So that is cosine. And then when we replace it, we arrive at this expression. So going back, remembering that our E field, we found that it was just going to be 2 ES in the S hat direction, this right here. Substituting ES, we arrive at this expression. Now, noting that there is no Z component, EZ is just 0, and my Maxwell stress tensor simplifies to this. The magnitude of E, it was just going to be this part right here, since S is a unit vector, and don't forget to square it when plugging it in. The next thing to figure out is what is the elemental area dA. Since I am using a cylindrical coordinate system, it would make sense to keep using cylindrical coordinate systems to describe the elemental surface area. And in cylindrical coordinates, a elemental surface area is SDS d phi. And for our case, since we're working with the lower charge, and by convention, outwards is positive, our area points in the z direction. So, since we're only focusing on the z component of the force, our zth component of the force is the integral of our zth component of t dot dA, which we're going to have to be tzz daz, and plugging in our stress tensor, and plugging in our elemental area, or dotting it with elemental area, we get this. And from this point forward is integration. So then I pulled out some constants, and the integral of d phi goes to 2 pi. We're left with s cubed over r to the 6th. Earlier, our script r is the hypotenuse of this triangle right here. So script r squared is a squared plus s squared. We want r to the 6th, so this just becomes cubed. And after replacing, we're left with this. We do a u sub, we let u equals s squared. This is our du s ds. We do a few substitutions, and you can pause for the details. We do a second u sub. We let w equal u plus a squared. We arrive at this integral. And at the end of integration, we are left with this. You can pause for the details. At the end of all the integration, we're left with this. And writing it back in notation, we're left with the force on the lower charge. For the upper charge, it is the signs simply just switch. To check this is okay, we got that the force points in the minus z direction. And if you remember, we're worked on the lower charge, which is down here. So this means that the force is downwards. For part B, everything is the same up to figuring out what your E field is at the XY plane. The difference is one of them is a different charge. Which one is arbitrary? So I chose the upper charge to be negative, and I will continue calculating the force on the bottom charge to keep everything similar. The difference then is that the S components of the electric field cancel out, and it's the EZ components that add up. So we're left with these relations. And after adding up our fields in the S and Z components, we're left with 2EZ. So in a more proper notation, E is 2EZ in the Z hat direction. I've written the different parts in blue, and we note that EZ is now sine theta times E. And then where E is simply, again, the electric field due to a point charge. So then the next question is to answer what is sine theta. And we refer back to this triangle here. Sine theta is opposite of hypotenuse, so it's just A over script R. And after that substitution, we're left with this expression. Remembering that E was 2EZ hat, when we plug in EZ, we arrive at this expression. So now the entirety of E is in the Z direction. So we know this new relation, and so now our stress tensor becomes this. Similarly, since I'm working on the lower charge, my elemental area points in the positive Z direction. The force in the Z component is the Zth component of T dot dA, which becomes Tzz dAz, and after plugging in this expression into here, and plugging in our elemental area, and dotting it with the component, we arrive at this expression. And from here forward, it's just integration. The bounds are 0 to infinity for S, and 0 to 2 pi for d phi, just like previous. After pulling in some constants and integrating phi, we're left with this expression. We're left with the integral of 1 over script r to the 6th, noting the same relation as last time. Plugging it in, you're at this expression, which is just another u sub. You can pause for the details. And at the end of integration, you're left with this expression. And then plugging it back into a more formal notation, this is our resulting force on the charge at the bottom. So, switching the signs of one charge, switch the direction of the force. And in this case, our force is pointing in the positive Z direction. So since we switched the sign, they would now be attractive. And we calculated the force on the bottom charge, so it makes sense for the force to point in the positive Z direction.